Hi, everyone. And thanks for coming to my talk. I know there's another great talk happening next door, which I would have probably liked to be in. But I have to be here. You don't, and thank you for choosing this. So I'm going to talk to you about front-end performance and the various stages of being a front-end performance optimizer. Not sure what stage I'm at, but who here considers themselves a beginner in front-end performance? Expert? One. Crazy person? One? Back there. All right. So my name is Philip. I work at a company called SOASTA. We do web performance testing, load testing, and performance analysis. I personally work on the performance analysis tool, what's typically called in the industry, it's called RUM, Real User Measurement. We collect data from web pages as users browse them, and we analyze that data and give insights to our customers on how people react to how fast or slow their website might be. And so some of this talk is based on insights from that, some is based on research I've done outside of that. I've written an open source library called Boomerang that does real user measurement. So it's a JavaScript library. You embed it in your web pages to collect data and send it back to a server. Prior to working at SOASTA, I worked at Yahoo at the exceptional performance team. So did a little work on YSlow and all of the performance rules that are on the Yahoo Developer Network. I wrote some of those. And some of those have changed over time. The web page has not. So what we'd like to do as performance optimizers is get the most benefit with the least effort, right? If you can sit back and do nothing all day and your code is just making things faster, that's the best. I mean. So before we get there, let's talk about bandwidth, right? Kansas City probably has the fastest bandwidth in the country right now. Who here has Google Fiber? Pretty cool. What's the bandwidth like? What do you get? What's the advertised bandwidth? Yeah, a gigabit. What do you think you actually get? 800 megabits? Yeah, okay. So I live in Boston. There's nothing different. I live in Boston, and my Comcast network is about 50 megs, but most people have AT&T or Verizon, which is 768 kilobits per second. The world is very different. So again, using Boomerang, we measured network throughput from users around the world hitting a server, well, which we hope was reasonably close to them. The US, you see, has a lot of people in that 2 to 6 megabits and going up. India, on the other hand, has a lot of people in the 512 kilobits to 2 megabits range. Hong Kong has a lot of fast users, and the world in general is fairly distributed. So different parts of the world have different network connections, and pages load up at different speeds. So depending on where your audience is, you might have to tweak your website differently. Right? Some places you can compromise and deal with a slow website, because it turns out that how users react to performance is also cultural, right? So we did some analysis on how different users from different parts of the world react to a fast or slow site. What you're seeing here is at what point 50% of the users decided to leave a page, right, based on how fast the page was. And some interesting things, Germans are the least patient, so they are always above 50%. Regardless of how fast the page loads. Canadians are the most patient. They're always below 50%, regardless of how long the page takes to load. And we asked some of our Australian friends why that is, and they said if you ever come to Australia and try to surf the web, you'll realize why. It's very slow surfing the web outside of Australia from inside of Australia. So people are just used to slow sites, and they'll wait for it. We also found that for the same websites on the same network connections, Canadians were 3 times as patient as Americans. It was pretty interesting. So how do you get your page from being really slow to really fast? Well, how do you improve performance, right? Get the most benefit? Well, the trick is to start with a really slow website. So if you have a fast website, you need to go and slow it down first. And, and then start measuring. Who here is measuring how fast their web pages take to load? All right, a few people. What tools are you using to do that? YSlow, all right. YSlow is a good tool. Google has something called PageSpeed as well. There's this tool called WebPageTest, webpagetest.org. It combines all of the tools that we have, and it runs your web page through one empty cache run and a full cache run, and tells you how long it takes to load. So it's a pretty good tool for measuring how long your page might take to load given a certain network type and a certain browser. It doesn't necessarily reflect what real users would see, but it's great when you're using it in development to compare different versions of your site, right? How fast was my site today versus yesterday before I made certain changes. So in this case, I ran web page test on the Midwest.io website, and you can see they got A's on a few areas and F's on a few areas. So some things can be improved, but a lot of things are pretty good. It also shows you a waterfall of when things started to load and when things ended loading. So you can easily tell what's actually causing you to put your load time to go out pretty far. And I think here the actual load time was at 8.5 seconds, but there's really only 2 or 3 images that were causing it to go out that far. So those are things, when you start measuring, you can actually see where you are and how you're improving and what's causing you to get to that point. We also learned in the keynote about this guy, Jean-Antoine Nollet, who did the first real user measurement experiment in 1746 when he found out that electricity travels very far, very fast. These days, we use JavaScript to do the same experiments on real users. So we have JavaScript in a browser that, in this case, we're measuring the load time of webpagetest.org, and we can see how long it takes to load for different users. As you can see, users don't tend to be the same. There's a huge spread of users in that histogram. A lot of users that are fast, but there's some users that are really slow. So no matter what you do, you can't make everybody's experience really fast, but you can try and make the bulk of your users' experiences really fast. And again, there's users from different parts of the world, so depending on where your target audience is, you may or may not need to optimize that, right? You might have really slow users from Bangladesh, for example, but you're not selling any goods to Bangladesh, so it doesn't matter, right? So, how do you get the most benefit? Turn on gzip. Who's using gzip? All right, those of you who aren't, go and turn it on today. It's free, all right? This is Netflix's chart. When they turned on gzip compression for their web pages, they reduced the bytes they were sending over the network by 50%, right? What does that mean? You're sending 50% fewer bytes, which means fewer bytes to reach the user, so it reaches the user faster. It means you're also paying your network providers less. Right? You're actually saving real dollars because you're paying your network provider, you're paying your CDN per byte or per megabyte that gets downloaded from their network. So this was a straight cost savings. Even if it doesn't make your pages faster, it's a great cost savings. But it turns out it does also make your pages faster. Right? So turn on gzip. It's very easy to turn it on. And in fact, there's a lot of complaints I hear that gzip costs CPU, that if I turn on gzipping, then the server needs to compress my content before it sends it out. Well, that's not true. What you can do is pre-gzip. So you gzip your content on your developer machines and then copy your gzip files over. In Nginx, you can say gzip static on, which means if a request comes in for a particular resource, first look for that resource.gz. If that file exists, just send that along as a gzipped one. If it doesn't exist, then look for the actual file, gzip it, and send it. So you get this for free. There's no CPU cost to it. You use less network, you use less memory, smaller file to hold in memory, and it's faster for the user. Right? A typical question that comes up is, what do I do about streaming content? Right? If I have my HTML page, or I have a Java application or a PHP script or Python script that's generating my HTML, how do I compress that? Because I'm sending it out chunks at a time. Well, you can also do chunked gzipping. So in that case, you have a gzip stream that you're writing to, and that generates content. It keeps compressing it as it gets sent out, right? So it's not impossible to gzip that either. I should mention, if at any point you have questions, ask them, because this is going to get more and more complicated. It's easier to get all your doubts cleared early on, right? Third step, optimize your images. So there's this really cool tool for the Mac called Image Optim. It's an open source tool. I believe it might also exist for Windows. If not, you can compile it. But there's also command line tools that do pretty much the same thing. In the case of Image Optim, you just drag all of your images onto this. It'll run it through a whole bunch of algorithms, figure out the best one that reduces its size a lot, and save those images with that new algorithm. So in this case, you can see I got 43% compression for one of them and 27% compression for the other two. So that's just reducing the byte size of the images that I store on disk, right? And so it reduces the size of images that get sent over the network and reduces the time it takes to send that data. You can also sprite. So a lot of images, sometimes a website has a lot of small images that are requested on multiple requests. You can combine them into a single image sprite, and then using CSS decide which part of the image to display. So that reduces the number of HTTP connections, and all of those images are just downloaded with a single connection, right? We'll get to that a little later in the talk. Part 4, all right? And you can see I'm running through this pretty quickly because it's the simple part. So cache control public, all right? This is something you put into your Apache config or your Nginx config. Just say, I want a far future expires header. So any of your static assets, cache them for a year, cache them for 10 years, right? Cache them for as long as you care about. The HTTP spec says 1 year. So I've set it there to a little less than a year. But if you cache it for a long time, what does that mean? That means it stays in the user's browser cache, right? If it's in the user's browser cache, the user's going to get it immediately. There are no HTTP requests, no network between the user and the resource. So the next time they visit your page, those resources are already there. They only have to download the main HTML, right? So that greatly reduces HTTP latency. So everyone who was at the beginner level has now been promoted. You're now an expert. You can go and ask your boss for a raise. Implement these 4 steps, and you will see improvements in your web page load time. That's why you need to start measuring first, right? Show your boss the before and after load times, and boom. All right. So now we're going to expert level. Any questions so far? All right. Serve your root domain through a CDN. So before we get to that, who actually uses a CDN? All right. Few people. Do you use your CDN for the root domain or for static assets only? Static? Both? All right, so one uses it for both, everyone else for static, and most of the people don't use a CDN. So what does a CDN do? I'll first talk about that. You, as a site owner, have 1, 2, maybe 10 web servers that you have control over, but you don't have them spread across the world. You don't have them sitting next door to your users, right? A CDN provider, on the other hand, it's their business to get boxes as close to the user as possible. So they'll have a box in every major city in the world. Typical latency between that box and a user will be something like 20 to 40 milliseconds, right? That's pretty small. So if you can get your content on those boxes, it means there's very little distance for that content to travel to get to the user. So serving your content through a CDN immediately gets you an improvement. You do have to pay for it. So there's a trade-off between that. If you're too small to afford a CDN, there are, in fact, CDNs that can do this for free, like Cloudflare, for example. Now, serving your root domain through the CDN does have a bigger benefit because normally we think that our root domain serves dynamic content. We can't put it through a CDN. But what happens is the user has a very slow connection to our root servers. But they have a fast, they also have a slow connection to the CDN, but the CDN is closer to them. And the CDN has a fast connection to our servers. So what happens is when the user makes a connection to the CDN downloads content from our servers really fast and then can send it to the user over their slow network, right? So we're taking that large distance between the CDN and our servers and sending data through that really fast, and then taking that short distance and sending it at the user's pace. So we're effectively reducing the total time it takes to download content, even though we're not changing the distance that the content has to travel, right? Furthermore, the CDN can have a persistent TCP connection open between their servers and your server, which means they don't need to open a new connection. They don't need to do a new DNS lookup. That's all latency that's getting cut out of the download time, right? So serving your root domain through a CDN is a big win. You should also make sure your CSS is on the same domain. Now, one of the rules we wrote on the Yahoo Developer Network was put your static assets, your CSS and JavaScript, onto a separate domain so that browsers can download them in parallel. That was true back in 2007. It's not true today, right? Browsers can make up to 20 requests in parallel, depending on the browser, so somewhere between 6 and 20 requests in parallel from the same server. So what you do is you put your CSS on the same domain as your root page, which means the browser no longer needs to do a DNS lookup to download CSS. Otherwise, what would happen in the past is the user would be downloading a page, and it'll take a few bytes before they get to the CSS link tag. At that point, the browser then needs to do a DNS lookup first before it can make an HTTP connection to download the CSS. Since you're serving it off the same domain now, that DNS lookup is taken out of the picture. That saves you easily between 100 milliseconds to 60 seconds, right? In the worst case, DNS failures could cost you 60 seconds. So that's a huge improvement on download time, right? There's a good article written by Jonathan Klein on the testing he did between serving CSS from a different domain and from the root domain. There's some people who also say put your CSS into the head of the document, right? Don't put it in a separate file. I'm in two minds about that. I think the caching that you get from putting it in a separate file gives you more of a win than just putting it, than the loss of a HTTP request from putting it in the same file, right? Split your JavaScript. So another one of the rules we'd put out was combine all of your JavaScript into a single file and serve that so that you don't make too many HTTP requests. Now we say, no, don't do that. Split your JavaScript into multiple files, right? If you want to get really crazy, you'd measure and say for different users, I'm going to split it into a different number of files. But to keep it simple, split it into 2 files. All of your critical JavaScript, anything that's required for the functionality of your page. So if you have a click handler and your page will not work without that click handler, put that into the head of your document. So put a static script node in the head of your document so that it starts downloading immediately. And it will block everything else on your page. Now, because of that, you want to keep a far future expires header so that it's highly likely that JavaScript is already in the browser's cache. And you want it to be as small as possible. So if you do have to download it, it doesn't take too long to download. And I'll talk about how small is small enough when we get to the crazy section. Right. Any enhancements should be loaded asynchronously. You can load them in the head. So you start loading them in the head, but there are various ways to download asynchronously. So browsers now have an async attribute for the script node. So you can say script source equals whatever and async, which means it'll download it asynchronously, but it'll still block the onload event. And not all browsers support it the same way, right? You can also download it just using JavaScript. So you use JavaScript to create a script node and load it. A lot of loaders do that. So that's one way to do it. But essentially, whichever way you pick, use that to download your JavaScript. Putting it in the document itself allows the page look-ahead parser to start processing it before it actually needs it. So that's one good way to do that. Audit your CSS. Who uses Google Chrome here? Finally, all the hands up. So if you open the web developer tools in Google Chrome and click on that audits tab, you'll find all of these things. And there's one called remove unused CSS rules. If you open that up, it'll tell you all the CSS rules that are not being used by the current page. So in this case, you see that 78% of, actually there's one file, fontawesome.css, of which 99% is not used, right? So we could reduce a fairly significant number of bytes. In fact, maybe the whole file, right, by getting rid of that. And 45% of main.css is not being used. So this one caveat is that this works on a single page, which means if you have a whole site that uses different parts of the CSS, it won't necessarily tell you that. So there's a tool called UnCSS that was released at FluentConf earlier this year. UnCSS is a command line tool. You pass it your website as an argument, and it runs through your whole website and tells you which CSS is used. So rather than tell you what's not used, it'll tell you what's being used. So you can just generate a new CSS file from that using only the rules you use. And that's a great way to get rid of unused CSS. There's also, so whenever you make these CSS changes, you might want to know if it's actually affecting your site. So I don't have a link here, but Stoyan Stefanov has written a tool called a CSS diff. So what it actually does is take a screenshot of your website with your old CSS and with your new CSS, and then do a screen diff of them. So it does an image diff and tells you whether there's any actual differences. It's a great way of doing an automated test of finding out whether your CSS changes broke your site or not. Parallelize downloads. So we can get higher bandwidth, and we are going to keep getting higher bandwidth. That's a financial problem, right? The more money you throw at bandwidth, the more you can improve it. The thing you can't improve is latency. So latency is bound by the speed of light, or the speed of electricity and copper, which is pretty much fixed by the laws of physics. And there are various people who think they can change that, but I don't think we can. So we're limited by latency. So one way to mitigate latency is to take all of these assets that might have been downloading serially and parallelize them. So we're saying, all right, since we have this really fast pipe, we can download many things in parallel rather than over a slow pipe where we had to download them in serial. So a lot of web pages which might have been a lot of rules that we came up with when Internet Explorer was still at version 6. Does anyone remember those days? It wasn't that long ago, right? So Internet Explorer 6 could only do 2 downloads in parallel from a single host. So we were forced to actually do everything serially. We're not limited by that anymore, right? Even Microsoft doesn't support IE6 or XP. So we should parallelize as much as we can, get that waterfall straighter, flatter, rather than spread out, right? And like I said, use sprites so that, because sprites combines multiple images into a single image file, they all download at once. Right? Flush early and flush often. So when you're writing dynamic HTML, so using a script to generate your HTML, it's oftentimes what you'll do is you'll buffer. So you'll keep writing stuff to a buffer, and when the whole buffer is done, you've finished generating your HTML, you then push it out to the client. What that does is now the client has made a request. It's now waiting for a response, but it's getting nothing because your server is still generating the HTML. And while it's waiting, what's happening is TCP is actually reducing the slow start window, which I'll actually get to in the next slide. What you want to do is, as soon as you know what that header should be, right? Is it going to be a 200? Is it going to be a 404? Is it going to be a 500? You should be able to tell that pretty soon, early on. You want to flush that buffer and send those bytes to the client. So the client knows that it can start doing something. Once you have the head of your document ready, flush that as well. So your client can then start parsing it and deciding, does it need to download JavaScript, does it need to download CSS, etc. Start those downloads in parallel. So all of this is happening in parallel on the client while your server's still generating results, right? If you're looking up a database and stuff, those are the expensive things that happen after the head is known about. So the head is sort of static content in your page. Flush that off to the client as soon as possible. So the initial congestion window. Now, who here knows about initial congestion window and TCP slow start? All right, so I've got an image to explain that. So let's say we have a request. This is how an HTTP request happens. First, the browser has to establish a TCP connection with the server. So it sends a SYN packet, the server sends back a SYN ACK, and then the browser sends an ACK. And with something called TCP fast open, it can also send its initial request payload on that ACK. So it sends a GET request, and then the server responds with up to 3 data packets, well, 3 to 10, depending on what your initial congestion window is set to. So what is an initial congestion window? So way back when the internet was invented, the inventors realized that A, network speeds are going to keep increasing over time, but B, there's always going to be slow clients on the network, right? So how do we make this network that is self-correcting, that detects if one end is too slow or too fast for the other end? So they designed something called slow start, where both ends would start off slow, and as they realized that the other end can handle a faster connection, keep increasing the rate at which they were sending data. That worked pretty well for connections like SSH or Telnet, where you're establishing one connection and sending a lot of data over that. With HTTP, it falls flat because what we're doing is opening one connection, sending a burst of data, and then closing it, and then opening another connection. So every time we do that, we're starting off slow, where we're saying we can only send 3 packets or 10 packets at a time, and then we have to wait for an acknowledgement from the other end before we can send the next burst of data. So there's this whole dead space where there's no data being sent. Now the problem is if you don't send any data, so if you don't flush early, the other end is going to think, hey, the server is too slow for the rate of data that I'm sending, so I'm going to reduce the data the window size. So instead of starting off at 10, I'm now going to start off at 5, or I'm going to go down to 3. And since that gets slower, you're now able to send less data at one time. How much data can you send in a single packet? Does anyone know? So typically about 1,500 bytes. Right? How many web pages can you fit in 1,500 bytes? So little known fact, when 9/11 happened, CNN was forced to fit their entire website into one TCP packet because that's all they could serve to a single user. And they actually managed to do that. So, but we can serve more than that. What we want to do is make sure that window size is large enough that we can actually send enough data. So you first configure your initial window to, there's a blog post there telling you how to do that. It's pretty involved for the slide, but essentially you set that to something like 10. If you're lucky, you're already using an operating system that sets it to 10. And then you keep sending data as fast as you know that you have it, right? So you don't wait too long to send data to the client. That way your window size is large enough. So that tells us also how large or how small each of our assets needs to be. So if we can do 10 packets at a time, at 1,500 bytes per packet, that's how large a file can we send in a single burst. A 15 kilobyte file, right? So typically when you combine your JavaScript and or your CSS into a single file, make sure it's below 15 kilobytes, right? After gzipping, of course. Because that means it can be sent on a single packet, and you don't need to wait for an acknowledgement to come back to send more data, right? That data's gone out, and you can forget about it. Another thing you could do is set this setting on Linux, net.ipv4.tcp slow start after idle equals 0. That basically means if a connection was open at some point and then closed by the client, but it remains open on the server, then you don't reset your window size. You just keep it at the last window size that you had, right? Use page speed. Who here uses mod page speed or ngx page speed? No one? Right, start using it. Right? It gives you a lot of performance improvements for free. You install it on Apache or you install it on Nginx. Is anyone using things other than Apache and Nginx? JBoss or IIS? No? One person? All right. So IIS or JBoss? So I know IIS also has a plugin. I don't know what it's called, but I'm sure the forums can tell you. But using page speed will do a lot of optimizations for you. It'll turn on gzipping automatically. It'll also decide what size your asset should be and what your cache interval should be like. So it's a pretty cool way to install something and do no work and get a lot of benefit for that. All right, now we need to relax because we're going to go to crazy land. Who thinks we were crazy already? So I want you to sort these in ascending order of signal latency. So by ascending order, I mean the fastest at the top and the slowest at the bottom. Which one is fastest? Who says, let's take a show of hands. Who says electrons through copper is the fastest? No one? Light through fiber? All right, a few hands. Pulsars? Many more hands. Station wagons? Smoke signals? All right, so I think pulsars were the clear winner for fastest. What about second? Electrons? Light? Smoke signals? Station wagons? No. Right, so light is second. What about electrons through copper? Third? All right. Between smoke signals and station wagons, which do you think is last? Station wagons last. Well, turns out smoke signals are actually second. So pulsars are the fastest because they light through vacuum. Smoke signals are light through air. The second fastest signal doesn't have very high bandwidth, but it's a pretty fast signal. Electrons through copper and light through fiber are pretty much the same, around 66% the speed of light through a vacuum. And station wagons are the slowest, but they potentially have the highest bandwidth. Right? You could you could stuff them full of 128 gigabit micro SD cards and speed down the autobahn or something. So you want to look for potential places to parallelize. Naturally, we can't, we could use the fastest medium possible, but we can't send much data on that, or we could use the slowest one, but it's not going to get there fast enough. But we want to look for potential places to parallelize, predict, or cache. Right? This is something that CPU designers learned in the 1970s. That if you want to make faster CPUs, you need to parallelize instructions. So we have now multi-core CPUs. They couldn't do it then because the technology didn't exist to make it small enough. But now we have parallel multiple cores. We can predict what's going to happen next. And we can cache whatever we know is going to be used often. So that's the same things we can do on the web. Right? We can parallelize downloads. We can predict what we need to download next before we actually need to download it. And we can cache things for as long as necessary. So prefetch assets required for the next page. How many of you know the typical flow a user goes through your website? Right? When they start on page A, they typically go to page B or C, right? And then go to so on. So if a user starts off on page A, you already know it's highly likely they're going to need the assets for page B. Let's start downloading them already. Right? So by the time they click on a link that takes them to page B, the JavaScript, the CSS, the images are already available in the cache. So that next download is pretty fast. Right? You can also use these pretty tricks that Chrome and other browsers are starting. So Chrome is the only browser that currently supports them, but other browsers are starting to support. The first is pre-render, which I think is pretty cool. So if you put this tag, link rel equals pre-render, href equals a particular URL on your page, what Chrome will do is as soon as the current page is finished loading, it'll start downloading that next page, the one you mentioned in that URL, not just the page, but all of the assets, and it'll start executing the JavaScript that's necessary. Right? So everything, basically the page's onload event is going to fire in memory, and that page is ready to view. So when the user actually clicks on that link, within a millisecond, it shows up on their page. Right? That's the fastest latency you can get. Right? In fact, Google does this with their search results. So the first search result that shows up on their page is generally pre-rendered. Right? So if a user clicks on the first link, it'll typically show up faster than any of the other links. It's a different matter that the first 3 links are typically sponsored links. So I don't know whether they do that for sponsored links as well. This can kind of mess up your analytics, right? If you're measuring analytics based on server hits, then you may actually have a hit for a page that was never viewed. So it's also likely the user just closed their browser at that point and did not click on that link. but the page was still requested and still showed up. So there's a few things you could do. In JavaScript, there is an onVisibilityChanged event. And when a link is loaded up pre-rendered, its visibility state is set to pre-render. Right? There are 3 visibility states: visible, hidden, and pre-render. At this point, Chrome is the only one that supports pre-render, but Internet Explorer and Firefox support the other 2. So you can tell whether a page has been loaded up but not displayed to the user. You can also tell, for example, if the user opened your page in a background tab and didn't actually look at it. So another cool thing you can do to decide whether you want to download assets or not, or actually start expensive JavaScript or not. The next one is link rel equals sub-resource. So let's say you have a large image on your page, but that image is downloaded pretty far down on your page. But you know that it's going to need to be downloaded. So what you do is you put link rel equals sub-resource at the top of the page. And when the browser comes to that resource, it'll start downloading the image and storing it in cache, but it won't render it until it actually sees an image link, or if it's a JavaScript or CSS, that actually references that link. And at that point, it'll just load it out of cache. Now, what happens if it's only partially downloaded at that point? It'll just continue loading at that point. So you don't have two requests made at the same time. And the third is a link rel equals DNS prefetch. This is a great way to tell your browser to do the DNS lookup for a resource that it may not need on the current page, right? It may need it for the next page, or it may need it further down in the page. So do the DNS lookup, and that saves you a fair amount of time. Right? And I mentioned onVisibilityChange. That's the event you can attach to onVisibilityChange. It fires whenever visibility changes. So if your page goes from visible to hidden, or hidden to visible, or pre-render to visible, this event is fired. Next thing you could do is post-load. So fetch optional assets after the onload is fired. So let's say you have a image carousel or something. You download all of the things that are required for the initial view, and then once onload is fired, start downloading the images that are needed for the next, when the user scrolls. Or let's say you have multiple tabs, background tabs you can download later on. Detect broken accept encoding. So it turns out that many Windows antiviruses disable gzip encoding for requests. So they'll look at the accept encoding header and they'll munge it. They'll change it to accept encoding or something like that. They'll change like the C to a D, or there's a whole bunch of things. I've documented them on that blog post. There's a whole bunch of creative ways they've munged the accept encoding header to maintain the same content length, but turn off gzipping. So what you want to do is detect this, because it actually turns off gzipping so you don't send compressed content. What you want to do is detect if this header is broken, and then send gzip content anyway. Right? So that'll kind of break the antivirus, but it'll make your page load faster. And I mean, you're not serving viruses, right? Anyone serving viruses? Prepare for HTTP 2.0. Today it's known as Speedy, but in a few months it'll be known as HTTP 2.0. Essentially what that does is it opens a single SSL-enabled connection to a server and downloads multiple assets on that. It can pipeline requests, so you can have multiple requests open together on the same connection, and it knows which response is tied to which request. So that kind of breaks some of our rules, because we said use sprites, but now you don't need to use sprites because HTTP 2.0 will take care of that. It's always SSL, so if you have multiple domains, you actually want to now serve it off a single domain so that you can use one SSL certificate to serve everything. And so it kind of breaks a lot of rules, but you want to prepare for that because it does, in fact, improve performance significantly. At the moment, Internet Explorer and Chrome are the only browsers that support HTTP 2.0/Speedy. Firefox, there have been commits related to it, but I don't think it's in the GA version yet. Opera, it turns out that since they switched to using Chrome's engine, you get all of this for free. But I don't know if you have Opera users for free. Learn how to use the black hole. So there's this page called blackhole.webpagetester.org. What you want to do is in testing, take every one of your third-party resources, so any JavaScript, any CSS, any widgets that you load from a third party, right? You have a Facebook like button, you have a Twitter widget, Google Analytics. Change your etc hosts file to point that host name to this particular host, and then see what happens to your web page, right? Or you can even do it through web page tests. So Patrick Meenan, who's the author of web page test, he's written a blog post on how you can program web page test to use the black hole, and then you see whether that particular asset failing. So do you want the Facebook like button failing to break your whole web page, right? Probably not. So this will tell you whether those assets are going to break your site or not. Understand the iframe loader technique. So this is a technique that I came up with along with some guys from Facebook and Meebo on loading assets, third-party assets that do not actually affect the page. So even if my server's down, for example, since I'm a third-party script author, if my server's down, it does not affect your page. And the same thing with if you're using the Facebook like button the way Stoyan's designed it to do. Finally, can you predict page load time just looking at your page, right? So I've got this fairly simple equation here that I'm just kidding. All right, that's the end of my talk. I have 0 seconds left, but I have a whole bunch of references on all the tools I mentioned here. Anyone have any questions? Yep.
I'm not sure if you mentioned it or not, but do you know of any good JavaScript libraries that will give you your end users real page load times?
All right, I'll repeat the question. So do I know of any JavaScript libraries that give you your real users end page load times? As it happens, I wrote one such library. It's the second one from the top, Boomerang. And that link has changed a bit, but that link will still work. But it's now lognormal.com/boomerang/doc. It's on GitHub. It's BSD licensed. Fork it. I accept patches if they make sense, and they follow the coding guidelines. Yep. Feel free to use it and let me know how you're using it. Any other questions? Right.
So for those of us who have to support a lot of users on like Internet Explorer 8,
Yeah.
I know that there's a huge bottleneck on that end, but what are maybe the best targets for supporting those users with what you've talked about here?
So a lot of the changes that you make are actually server-side, right? Turning on gzipping is immediately going to have an impact for users on IE8. You're going to reduce the number of bytes that are downloaded. IE8 is still way better than IE7 and IE6. So you straight away get some things for free just by the fact that they're not on 7 and 6. Parallel downloads do in fact work. They bumped it up at 8, so you can do 6 parallel downloads versus 2 in 6 and 7. So that's a great thing. Another great thing is that SSL actually works. So you can have the same host name that is both SSL and non-SSL, which did not work on previous versions. There are some things that don't work. So, for example, all of the pre-rendering stuff and all doesn't work. But you can use JavaScript to do that. So we generally stick JavaScript into the bottom of the page that might load resources after onload that are needed for subsequent pages, or just make your page leaner. So sometimes design your page that doesn't need JavaScript and then use progressive enhancement to add that on. Anything else?
So instead of caching for a really long time on the browser,
Yep.
is there anything you could say about e-tags?
All right. So the question talks about e-tags, and I'll explain what e-tags are first. So there's an HTTP header. There are 2 HTTP headers that deal with caching. One is the last modified header that tells you when this particular asset was last modified. Another is an e-tag, which says it gives you a signature for this particular asset. Now, if either of these 2 headers are present in a response, then the browser holds onto that, and the next time it makes a request, if it sees the last modified header, then it'll send a conditional request saying, send me this resource if modified since and that particular date. On the other hand, if it sees an e-tag, it'll send a header saying, send me a request if none modified and give the e-tag. So the thing with e-tags is the default e-tag implementation on Apache, at least, uses the inode number on disk of the file, under the assumption that if you change the file, its inode number is going to change. It so happens that if you use multiple servers, the inode numbers are different across multiple servers, so the e-tag is going to be different across multiple servers. So if a single request comes in to one server and then goes to another server, you're going to have different e-tags. So if you can change that, if you set your e-tag for static assets, well, for static assets, just turn off e-tags. In fact, I also say turn off your last modified header, because you don't want conditional requests coming in anyway. For dynamic assets, something like a web service or a PHP page or something like that, you can generate your e-tag based on the content or based on something that you know about the content that will change if the content changes. So in that case, you can use an e-tag and send that out to the client, but only if you're generating it yourself. And then that reduces the number of bytes sent, but does not reduce the number of HTTP requests. So you still have to make an HTTP request to find out if that resource has changed or not. So as far as possible, try and turn off last modified and e-tags headers. But if you absolutely have a resource that you know can benefit from it, then use only e-tags. Right. Does that answer it? Right. All right.
All right, thanks again, Philip.
Thank you.
And how about a round of applause real quick?